There we go. Okay. Pull up our Brightspace account here. For those of you that haven't, if you could, it would be better if you don't mind, is to upload quiz 8, which was the one that was take home before or spring break, just to try to keep us all on a our schedule. So that would be good. If not, for some reason, I will take it next Tuesday as well. I don't want everybody to fall too far behind. So we're only doing 2 sections. And so we're going to do section 6.8 today. So we probably won't be here for the whole class period, which is probably a good thing because it's remote. And we were going to have a quiz today in class, but obviously since we're not in class, I made this one take home as well. And you could find it under content here. And if you go all the way down to the bottom, you would find the take home quiz right here. So this would be due on Tuesday. So you have, like all the take homes that I've given, you'd have Briss bringing in the class on Tuesday. I would prefer to grade it with pieces of paper. So if you don't have a printer, don't worry, just write it out on regular paper and bring it in. For some reason, you're going to miss class that day, you could always upload it as a single PDF file, and I'm happy to grade it that way as well. So, any questions so far? Okey-doke. Looks like it. That's a trig. We don't want to get back that the algebra. So what we're going to do today is talk about some what I would consider more of a science application for exponential functions. So if you look at in chapter 6 and section 6.7, it talked mainly about the idea of money and compounded interest, which is modeled using an exponential function. So what we're going to do today is more of a science application. And you'll see in this case, the base of the exponential function is going to be that letter E, or the natural base. And so we're only going to do a couple of these. If you look if you did look at the ebook, there's like 5 or 6 different applications, and they're all about the same, and they use a slightly different equations. And so what I decided to do is to pick the ones that are the most popular and more of the easier equations as well, to give you an introduction on using exponential equations in science. So the ones that we're going to do are called growth and decay. And we talk about it in an exponential sense. So it's usually called exponential growth and exponential decay. And what we mean by the exponential growth and decay are graphs that look like this. So on the left side here, hopefully you see this graph where this X, or the horizontal axis, is actually going to be time now. And if you remember when we did these on Tuesday, time was always in years when we talked about money, right? And compounded interest. Here, time could be minutes, seconds, hours, or years. So you have to read the problem to see what it is. And then this would be decay. And so you could see growth goes up, right? So you're going to grow without bound. And here you could decay as it gets closer and closer to zero as time goes way out. So these are the two applications that we're going to focus on in this section. So let's start with growth. So we're going to start with growth. And let's see. I want to use the same letters. Use different letters here. Let's see. Okay. Yeah, they use different letters. Most of the time, it looks this way. The amount of whatever we're trying to measure, and A stands for the amount, A of T, is the initial condition, which would be A0. And E is our base. That is 2.71727. That's the natural base. And then K is our growth rate, and T is time. So A0 is the initial condition. K is going to be positive, and it's going to be the growth rate. And T is going to be time. And depending on what we're measuring, as I said, T could be from seconds all the way up to years. So what do we mean by that initial condition? Well, remember when we did the money problems, right? That was our initial principle, right? We started with $1,000 or, $50 or $1 million, whatever we start with, right? That would be our initial condition. And this is the same idea. And this is a growth rate that's what we call uninhibited. So it'll go to infinity as time goes on. And when the initial coronavirus came around, it was an uninhibited growth because there was no immunity virtually anywhere. And as things changed and vaccines came on board and people got it, then the models ended up being a little bit different. But most of these ended up being modeled with exponential equations. And this growth rate depended on how contagious whatever variant we were dealing with. And so I actually looked at a couple of these. It was a while ago now, and it didn't look as different as what we're going to talk about. So there's some practicality to this. Any questions so far?
Not at the moment.
Okay. So I'm going to take a problem right out of the book here. So let me kind of show you how these things might be structured. So this is called a bacterial growth problem. You can think about this like in chemistry, I think they call them petri dishes, where you would put initial bacteria in there and measure it and see how much it growed, maybe every hour or every minute, depending on the bacteria. Typically, it looks like this one is in every hours. So let's walk through this problem and see how you get this all set up and how you solve this. So this one says a colony of bacteria increases according to the equation that I had up there. And see, they use N, but we'll use A, which is the number of cells. T is going to be in hours. And so it says if the bacteria doubles in 3 hours, you could use this to figure out what K is. So let me show you what I mean. Let me pull up these equations. So I'm going to use the letter A in this problem. It uses N, but it says that the bacteria doubles. And what did it say? 3 hours. So how do you measure that? Well, you'd start with a bacteria, say like you started with 10 grams, right? And you measure it. And then 3 hours later, you measure it again, and you see now the weight would be 20 grams. That's what we mean by doubling. So once you know that, and you're modeling it using this equation, you'd be able to calculate what K is. And let me show you how to do that. And you'll see that this technique is used quite a bit. So if we start with A0, right, and we double it after 3 hours, we would have 2 times A0, right? So if we started with 10, it would be 20, right? If we started with 50, to double that, it would be 100. So that's the concept of this doubling time. And when we do decay, we're going to do something called half-life, which is how long does it take it to decrease by 50%. So when you set up this equation, it would look like the amount is going to be 2 times A0, right? If it's 10, it would be 20, if, and so on and so forth. So algebraically, we could write it this way. And how long does it take for it to double? 3 hours. So we could put 3 in for T. Cool. Questions? All right. Well, the first thing you could see we could do here is we could divide each side by A0, right? And this works every time. If you started with 10, and divide by 10, you would get 2 on the other side for 20, right? So these would cancel. And so this equation would simplify to 2E and then 3K. I'll just put the 3 out front. So the question is, how do we solve for K, right? We're solving for the K. Well, here's what I was kind of warning you, is this is where these exponential equations where logs become a way to solve these. How do we bring K down so we could do some algebra that we know how to do, right? Well, the strategy here would be, we're going to take the log of both sides of this equation. And because we're using base E, the arithmetic is easier if you use natural log. So if you take the natural log of both sides, it would look like this. Natural log of 2 equals natural log of E to the 3K. Any questions on that? So from that properties that we talked about, you could rewrite this by bringing this in front of the log, right? And so it could be 3K natural log of E. And you'll see in this section, you're going to use this technique over and over again. And the reason why we pick natural log is natural log of E equals 1, right? The log of its base is always 1. And so what does K equal? Well, if you divide each side by 3, K would equal natural log of 3, or excuse me, not 3, natural log of 2 divided by 3. So what is that number? You got to get your calculator out, right? So if you got your calculator out, it would be 0.23105. Any questions on that? Silence means no. Okay, so now we have the calculation for K. And so here's what our equation looks like. A of t equals A0 E. Now we know what K is, right? 0.23105 times T. So a lot of the times you don't know what the growth rate is until you do an experiment. And basically the way they would do this in a lab is put the certain bacteria in the Petri dish, like I said, and 10 grams, 100 grams, whatever the right value to start with, and then keep measuring it until it doubles. And then they would do this calculation to find the growth rate. So anybody getting into medicine or biology or anything? You could be using this type of technique. So now once we have this equation, say like I asked you this question. Say like you start with 10 grams. So that would be A0, right? Then how much do you have after 10 hours? So now you put 10 grams in your Petri dish and you let it do its thing, and now it's growing, right? According to this equation. So how do you do this? Well, this would be A of 10 hours, right? And so what's A0? That's our 10 grams. And then it would be E to the 0.23105. And then you plug in 10 in for T. Here you definitely need your calculator. So this would be 0.23105 multiplied by 10. And so this part would be 10, and believe it or not, it's, at least on my calculator, is 10.08. Rounding to 2 decimals. So after 10 hours, it looks like it's almost a factor of 10 bigger, right? Because 10 times 10.08 would be 100.8 grams. Any questions on that? Oh, yes, maybe. So why don't you try this one? Try A of 5. Because I found that one of the things that if you haven't used your calculator to do these calculations before, it can be a little bit tricky until you get the hang of it. So while we're all here together, why don't you try this one? I'll give you a minute to see what you get on your calculator here as I do it as well. Everybody get an answer yet? Who wants to share? Okay. Well, when I did this calculation, I got 3.17 and some change. And if you multiply that by 10, you would get 31.7, say 5 grams. So you could see that this one was a little more than 3 times what we started with. You got a question, Chella?
Yes. How do you type it into your calculator?
Yeah, I wish we were in person. It depends on what calculator you have.
Okay, I'll just remember and then I'll just ask you next Tuesday.
Yeah, or we're going to get done early today. Like I said, we're only doing 2 sections today, and we're not even doing the whole section. So maybe I could help you after class too. If you have a camera, maybe I could see your calculator.
Okay.
Great question. That's what I mean. And I wasn't being facetious about it. Until you figure out how the technology works, it took me a couple tries when I first dealt with these exponentials on how to use your calculator. And then when you get a new one, it's even worse because then you got to learn it all over again. So that's why mine's nice and old. So these would be kind of the main problems of the exponential growth. So for example, let's just pull this one up. I feel like we just talk about the growth one more time, right? We'll call it A of t. Let's do one more K calculation. Say, like I said, that whatever bacteria we're talking about, it doubles at 5 hours. So again, this is the one where you calculate K. So what we mean by doubles is that if you start with A0, you're going to end up with 2 times A0 at the end of it, right? So if you started with 15, you would end up with 30. So we always write it this way. And now this would be 5t. Whoops, not t. We're calculating K. It'd be K times 5. So again, the same strategy here. These will cancel, right? You divide each side by A0. And you end up with 2 equals e to the 5 times K, right? And so you see the strategy. Take the natural log of both sides. And then you can bring the 5K out front. And so you're going to be doing this a lot in this section. And again, use natural log because it makes the arithmetic easier because that number always ends up being 1. And so in this case, K is going to be natural log of 2 divided by the number 5. So just depending on that, you'll see that the doubling time will always be natural log of 2. If it was tripling time, it'd be natural log of 3, and so on and so forth. So what would this be? Natural log of 2 is 0.69, 5 divide. So you see K is a little bit smaller now, right? Because it took longer to double than 3 hours. And as that number gets closer and closer to 0, right? What ends up happening is the growth is slower and slower and slower. And if the number is big, then it grows really, really fast. Have I got anything for me? So that's this one here. So this is the exponential growth right here on the left side. And you see where A0 is, that's our initial condition. I think in our one that we did, we had 10 grams, but it could be, whatever you're measuring. So the other one that we're going to talk about is this one here, the exponential decay. And again, you're going to start with an initial condition. And you're going to end up getting, as time goes on, it's going to get smaller and smaller. That's what we mean by decay. And I'm going to show you a problem that I actually had one very similar when I was taking college algebra many, many decades ago. And I actually missed this problem, so I like doing it for you because I feel like they try to trick you sometimes. So you have to be, a lot of these are going to be word problems where they're going to give you some information and then you got to put it in the equation. So before we do that, let me just pull up the whiteboard again. So this is the same equation for both the decay and the growth. And growth is when K is positive. So it's going to be greater than 0. That's when it grows. But when it decays, you'll see K is going to be less than 0. So this is the one that we're going to do now in the decay. So you're going to start with, say, 100 grams of something, right? And it's going to decay over time to, say, 50 grams. That's what we mean by decay. So A0 is going to be the biggest number in this case, what you start with. Does that make sense? I know these online classes are hard. So one of the things that is a classic exponential decay problem is this idea of trying to figure out how old things are using carbon-14 dating, where this element, carbon-14, has a very, very well-defined decay factor, and it's really long. So if there's some carbon-14 in a fossil, for example, being able to figure out how much of the carbon-14 is left, you could have a very, very good estimate of how old something is. And so this is a classic one that I think every college algebra student ends up, and this is carbon-14 dating. And the Dead Sea Scrolls were, even when I was taking college algebra, very exact same type of problem. Seems like the one that you see a lot. And so you see this idea of half-life right here. So the half-life is when, if you start with 100, after 5,750 years, you only have 50 of it left. See what we mean by half? So whatever you start with, you get cut in half. And that's a little bit trickier than doubling, I think. Oops. Sorry about that. And so the way that they have this set up, I find it really tricky. So it says the archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls lost 22.3%. How old was the wrapping? So let's write down what we know. So it says it lost 22.3%, right? So remember, you start with 100% is the way they have that set up. So if you lose 22.3%, this is what you have left. And that's what made it tricky. So that's actually what this ends up being when you do the calculation. But before you can even do the calculation on how old the Dead Sea Scrolls are, what is K? Well, you have to calculate K. And we calculate it using the half-life. And they say that the half-life is 5,750 years. So how do you set the equation up? Well, you start with A0, right? And so say like A0 is 100. So if half of that, right, you would end up with 50. So instead of writing it that way, we just write 1/2 A0. See the difference? When it's doubling time, this is a 2. And when it's half-life, it ends up being 1/2. Any questions on that? Same theory, right? Now we plug in E. We don't know what K is. We need to calculate that, right? And so that would be 5,750 years. Any questions on that setup? So, same strategy. Divide each side by A0. So you end up with 1/2 e to the 5750 times K. Guess what you do? Take the natural log of both sides. So it'd be natural log of 1/2 equals natural log of e to the 5750 times K. So you could rewrite it. Natural log of 1/2 equals 5750 K. Natural log of E. That's why we use natural log, make the arithmetic a little bit easier. So what does K equal? K equals natural log of 1/2, and you'll see that actually is a negative number. And when you plug that into your calculator, you would get a negative number there divided by that many years. 3050. Yeah, 50, sorry. All right, let me get out my calculator here. 0.5 natural log is minus 0.693. So it would be, I just keep the decimals that they have divided by 5750. And so it looks like K would equal minus 0.000120 and some more. So this was a little bit tricky because, you know, how many decimals do you keep? Typically, this should be good enough, right? Especially if the next number is 0 after that, when you do that calculation. I'm pretty sure that when you do this in my math lab, it'll say round to the nearest blank. And so that'll help you as well when you do the calculation. Any questions on this?
No.
Yeah. All right, so let's set up the equation now. So if you set up the equation, you get A of t equals initial condition E minus 0.00012 times t. That's a point there. And so to finish the problem, it says, well, how old is the Dead Sea Scrolls if you lose this amount, which means you have this amount left? Because if you start with 100%, you're going to have 77.7% left. And I know when I can't believe I still remember this, but when I did this problem and decades ago, I used the wrong number. I used this one. I don't know why I still remember that, but I do. All right, so how do we stick all these numbers in? So again, same theory here. You're going to be sick of natural log in this section because you have to use that in virtually every calculation. So in this case, you start with 100%, which is A0. You have this. And then just like the interest rate, we talk about it in percentage, but when you plug it in, you want to plug it in as a decimal. So it looks like that. Any questions on that? So you see these cancel again, all right? And so you would just have natural log of 0.777 on one side, and then natural log of e to the minus 0.00012 t on the other side. So you could rewrite this as minus 0.00012 t times natural log of e, which is 1. Like I said, I think you'll get sick of doing this calculation. There's not that, I don't think there's that many problems in this section. So what does t equal? Natural log of 0.777, which is a negative number, divided by another negative number, 1, 2, which is k. If I get my calculator out, let's see what we get. Natural log 0.00012 divide. So I ended up with 2,102 years. And if we round to 1 decimal, 0.6. So if you round to years, looks like that's what the problem asks for. It would be 2,103 years. We got any questions? Comments?
No, Professor, not at the moment.
What do you think? Not too bad? I think figuring out how the calculator works will be as much of a challenge as doing the algebra part of it. So like I said before, there's some other applications in this section that I just decided to skip. There's something called Newton's law of cooling, which guess what is another exponential function. And you just solve it the exact same way. You plug in the numbers, take the natural log, and So I decided to skip that. So there's no homework on that, and I won't ask you a question on that. And there's also this logistics model. This one's a little bit more complicated, but again, once you plug all the numbers in the right spot, you still have to take the log of both sides and do that same calculation. So I decided to skip that as well. So when you take a look at least this last section, I only do part of it. So, and excuse me, the part that I picked is definitely the most common. But like I said, after a while, all the calculations are exactly the same. And so I could show you a bunch of different equations. And then the harder part is to figure out what equation to use, where it's nice. You have exponential equation. K is positive, meaning growth, right? And K is negative, that means decay. So, anybody got any questions? Like I said, I knew, well, if we were in class, I would give a quiz. That's why, but we're not. So let me just pull up, kind of show you a couple of the problems and my math lab here, just to show you what I mean. So this is the first problem from section 6.8. So they use P, and you can see P of T. Can you see that up there? Maybe I can make it a little bit bigger. Let's see. There we go. So you can see here's our exponential equation. They use P instead of A. But you can see the initial condition is 100, right? And it looks like T is in days. So here's our equation, 100 E, and it says 0.07. So that's K. So they give you K, which is kind of nice, right? So they give you K here. So here you see the last one's the doubling time, right? So what do you put in to calculate the doubling time? Well, what's twice of 100? 200. So that's what you would plug in to do that calculation. So the first one, when you plug 0 in, you're going to get the initial condition. So that would be 100. The growth rate is 0.07. That's K. And then just plug in these numbers, right? Plug in 10 for T, you know, and then here you want to calculate T by plugging in 170 for the amount of insects. Anybody got any questions on how to get any of that set up? So here they give you K again, which is really nice. So that's not too bad. Where's one where you have to calculate K? So this one here, they're going to be giving you some information where you calculate K, like what the doubling time is, like we did in the first one. So. I don't want to keep you here any longer than we have to. So I'm happy to do another example if anybody has any questions. But really, that's this section. You know, I wanted to give you a feel for how to do both of them, and went over a little bit of the homework. So like I said, around 1 o'clock, I would have probably given the quiz, or excuse me, 2 o'clock. And we're pretty close, not too many questions. That's why we're almost done. Anybody got anything for me? Okay, well, I'm going to turn off the recording.